Yesterday, whether or not you were here, as you checked out the video, you would have seen that I pulled up on Desmos a polar grid. You can change back and forth between rectangular grid and polar grid. It's way up here in the little wrenchy thingamabob. So that's the one that we normally do, but there's also a polar grid. And a polar grid, well, it works a little differently. Do you guys see grid marks that go vertically and horizontally at all? No. But could I? Thanks for the yes, but what could I do? Could I go tick marks? Could I go tick marks still? And it still matches up with something? Yeah. Yeah. Now specifically, if this is 2, I think they're going by halves. So that'd be 1, that would be 2, that would be 3, that would be 4. So they're going by halves. But I could go tick marks horizontally. I could also go tick marks vertically. And what do you see that the tick marks vertically and horizontally measure up with? The circles. Because the circles are the size that they are because of their radii. And isn't the radius in any direction going to be the exact same? Now, why aren't there vertical lines and horizontal lines? Well, radii or radials don't go horizontally or vertically, they go circularly, right? But if I'm on the axis, I can still do tick marks, and they can still be helpful. So what was one of your first points? Now, I know I did not want you to draw this. However, let's see how it should have looked as far as graphing the first point in this table, and then we'll see if we can do it without all those concentric circles. I have tick marks. The tick marks, I just have my tick marks going by 1s and 2s and 3s, etc. Just by going by 1. I wonder why I went out to 8. Because I have a radius of 7. And I didn't just go out to 8 in one direction. I went out, if you guys counted, which maybe you probably didn't, I went out to 8 in every direction. But, what's the first point? 7, 0, which means the angle is 0. The angle, if you guys need, peek at this really quickly. Angles, 0 starts where it always starts. Sometimes we call it the positive x-axis, but do you remember the special name now in polar mode? It's in your notes? Polar axis. It's the axis, but it's the polar axis. Polar mode. Anyway, whatever. Polar axis, 0, 30, 45, 60. We measure from the polar axis. Okay, so if 0 is here, then I don't even need to worry about any concentric circles, do I, for the first one, guys? Because couldn't I just go ahead and put my point at 7 out on the 0 angle line, right? Okay, so that one wasn't too bad. But the next one we're going to have to think of a little bit more carefully, because if I needed 3 and pi over 4, well, let's go to my polar graph real quick. Pi over 4, wouldn't that be right here-ish, right? Okay, so if pi over 4 is here, this one's going by 15s, 15, 30, 45, 60, 75, 90. If 45 or pi over 4 is right here, then, guys, if I had all of my circles drawn and we had all of our tick marks, how could I get to pi over 4? Well, just turn. But how would I get to 3? Go out. Out. Well, wait a minute. It's not like up. That would be something different. 1, but it's out 1. Connecting those two. Right? So I can go out. Hold on, sorry, that's a half, right? So out a half, out 1, out 1.5, out 2, out 2.5, out 3. How does this correspond to 3 on the axes? Is it over 3, up 3? No. But think about the 2 3s, this 3 and this 3. And think about connecting them with a circular segment. And what I'm looking for is where does that circular segment intersect pi over 4? Booyah, point. 7 sadly outside of that. Let's go back to here because it's going to be easier. So what do I do here without having to draw all the crazy things I might not need? Can't I just go ahead and say, oh, hey, isn't pi over 4 cutting this guy in half? And couldn't I go to 3? And go to 3 and connect it with a circular segment and say, oh, sweet. Where does it intersect? Do you think when you get really good, you might not even need to draw that? So I think of going up 3, that's a radius of 3. Going out 3, that's a radius of 3. Okay, my units aren't perfectly the same as far as the spacing, but that's all right. It gets the idea. Connect with a circular segment and then be like, oh, hey, right there. So how are we going to do the next one of 0 pi over 2? Isn't anything with 0 going to be at the, used to be called origin, now it's called a pole. Right? Okay, cool. I want you guys to go ahead and start to graph the next point if you have not yet already. You're supposed to have 3 points. So now, Jason, try to graph this one. What angle is 2 pi over 3? What quadrant is that, guys? So is anybody thinking about how that's a 60 degree in like the second quadrant? Cool. Anybody remembering right about now what a negative means with radii? Yeah, you see someone you don't like in the hallway, you're like, I'm backing away, right? The other direction? Not necessarily, you probably shouldn't literally do that, but a scowl isn't really appropriate, and a pasted on like isn't really appropriate either. Might be a better idea for yourself as to why you don't like them. But coming back, yep. If I'm not going towards 2 pi over 3, if I'm going away from 2 pi over 3, where am I actually headed? Backwards, away, or towards 5 pi over 3, right? 2 ways of looking at it. We could be going positive 1 in the 5 pi over 3 direction, or negative 1 in the 2 pi over 3 direction. Either way, we will end at, did you guys do the little rotating thing with 1 and figure out the intersection is about there? Did you do the rotating thing? And you graphed it? So I can see it? Cool. Yeah. Because from Thursday, nope, from Tuesday, today's Thursday, remember we talked about how positive r's go towards angles? So if it was a positive one, I go towards 2 pi over 3, but since it's a negative one, I'm going the opposite, or 180 degrees. So in this one, since it was a negative 1, I'm not going towards 2 pi over 3. I'm going opposite 2 pi over 3, which means 1 in the other direction, 180 away. Okay, what's the next one? Negative 3 pi? Well, isn't pi this way, though? So wouldn't negative 3 really be going towards 0? So wouldn't that just be right there? Oh, this is weird. So I have this. And somehow, if you were watching us yesterday, we realized there's some sort of like rotating thing that happens, and maybe it went out something like this. I'm doing kind of random angles. I'm doing pi over 3s, I'm doing pi's, I'm doing pi over 2s, pi over 4s. It's very possible that this one actually should have had some symmetry, and if it had some symmetry, maybe at the pi over 4 over here, maybe it would have actually been about the same distance out, which would have been 2. Oh, no, hold on. That's okay. I haven't given you guys a function. We'll just do that. What's 3 pi over 2? Which means you're back to what? Oh, I'm not exactly sure how. And then 7 pi over 4, isn't that in the 4th quadrant somewhere? Should be here. Is that a positive or a negative? So is it going towards or away? So I'm going 1, 2, and 3. Oh, well, I just came from there, so I guess I'm going there. And then what does the next one say? Oh, I think I made a shape.
An avocado.
Hey, almost. If only he was a little bit. What? Rains?
What shape you're aiming?
Okay. This is actually something called a limaçon, but we'll talk about him in just a second. But guys, do you get the idea of graphing points without needing to have all the crazy concentric circles all pretty and evenly spaced and whatnot like we did yesterday or 2 days ago? Okay. All we need is what we need. All we need is the angles that we're actually referring to, and all we need are the radii we're actually referring to, and all we need are the circles that are actually being accessed. So I'm not going to have you draw concentric circles. Yeah. So you're backing away from the angle, aka turning and going the opposite way, which you can also think is going 180 degrees the other way.
A better analogy than seeing someone in the hallway is using a wasp hive.
Oh, that would be negative. Good call. Good call. That wouldn't be as sad. A wasp hive. Guys who were gone yesterday, we had some really important formulas about how, you might want to take a picture of it if you didn't get it in your notes, about how r's and thetas and x's and y's all relate, because x's and y's is what we're used to, rectangular points. R's and thetas is what we're doing now. X's and y's what we're used to, r's and thetas is what we're doing now. So if they give you an x, y, and you need to go to an r theta, maybe these formulas would be helpful. But if they give you an r theta and if they want an x, y, maybe these formulas would be helpful. But they all come back to what? A right triangle. They all come back to Pythagorean theorem stuff and trigonometry stuff. And so yesterday we ended class with doing some conversions of points. And those conversions of points included one polar one to rectangular and one rectangular one to polar. But there were, whoa, 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 why are there so many? Okay, hold on. How would you approximate negative root 3 root 3? Negative. If it's an x that's negative, what direction do you go? To the right or to the left? To the left. And then if it's a positive y, you go? So whatever this is, I'm going to the left a certain amount and I'm going up a certain amount. This point should be according to the x and y in the second quadrant. Done. So how on earth, after I use Pythagorean theorem to say, okay, well, if this is my adjacent and this is my opposite and I want my hypotenuse, which we found to be our r, if I want my angle, which I found to be a 45 because tangent ended up being 1 and square root of 3 over 3, 1 square root of 3 happens at 45s. I asked the kids yesterday, and it took them quite a bit of time to figure out how to make points from that known quantity of r, could be a positive or a negative, and that known increment of theta. It's some sort of 45. How did they come up with, how did we come up with so many different points and we could have kept going? Guys, what quadrant is this 45-degree angle in? Second. Third? No, the top one. What quadrant is he in?
Third.
Nope.
Wait.
Positive 225 is in the third. Where's negative 225? It's in the second quadrant. So if this is the second quadrant, wait, where was my point at? Oh, so if this is the second quadrant and I want to go to the second quadrant, my radius needs to be positive, so I go in the right direction. Where's this angle? This angle is in the second quadrant, and I need to go towards it, positive radius. This angle is in the second quadrant, and I need to go towards it, a positive radius. This angle, ooh, what quadrant is he in? Fourth quadrant. So why is radius negative? Because we need to back away to get in that second quadrant. Yeah, Adam.
So the negative angles like go into the quadrant where the point needs to be, then the radius can be positive.
Has to be positive. If it was negative, you'd be going the wrong way. Yeah. How about what quadrant is negative pi over 4? Fourth quadrant. So where do I need to go? Back away. I need to back away. So whenever you're making a polar point, you need to think about what angle are you choosing, and based on what angle you're choosing, do you need to go towards it or away from it? Could you sometimes be using the positive value of r? Yeah, if you want to go towards the angle. Or could you sometimes be using the negative value of r? Yeah, if you want to go away from the angle. How many polar points are possible? Why a lot? Didn't we just go through all the different options? coterminal. What if your little guy on the pole, remember the origin's called the pole, on the pole, what if you spin him, and then send him off? It'll be a little jagged, but couldn't he still land in the right spot? So coterminal angles are actually infinitely many polar ways of getting to a point. But does that mean any and every polar way will get you in the right spot? Nope. Got to be careful. Got to be careful that you know what angle you're talking about and you know what direction you need to head from the beginning. Now, in this one up here, 11 pi over 6 was in the fourth quadrant. It was a negative radius, though, which sent us back to the second quadrant. But we just actually ended up plugging in our equations from that right triangle that some of you guys just took a picture of a second ago that you need to get those formulas down from. We just plugged into our formulas of r cosine theta for x and for y. Oh, that is x, sorry. R cosine theta for x and r sine theta for y. And it happened naturally the way it needed to. We actually had a picture going the wrong way. I said 11 pi over 6, radius of 3. I was in the fourth quadrant. My x, though, said, no, you're going left, and you're going y was positive, up. So this formula will land you in the right space, which ended up working out with what we had, because this fourth quadrant angle and negative radius, we should have gone back. But this one, we kind of have to be a little bit creative and careful with. Okay. What's something we didn't get to yesterday? We got to converting points. We did not get to converting equations. We got to converting points, but we did not get to converting equations, which is why I let you guys take a quick picture of that whole right triangle thing, because we're going to have to use them again. So with this whole page, I don't actually know what's easier, to be honest. Teaching honors pre-cal kids this, reviewing this with calculus BC kids, you don't really see it in AB, you don't see polar until BC. Aww. I kind of just keep on coming back to, if worse comes to worse, at least knowing the triangle. I don't know. The more and more I do this, I keep coming back to, if worse comes to worse, know the triangle. But for some of you, I know your brain works better from memorizing. So we do have that page on the other side. We do have that page on the other side. Or 2 pages back in your notes. Okay, if x equals 10, and I need to get the x out and polar stuff in. Who's allowed in? R's and thetas. Oh. If you knew the triangle, maybe you could say, how do I get r's and thetas from x? What would relate r with theta with x? What would relate hypotenuse with angle with adjacent? What would relate hypotenuse with angle with adjacent? Come on, you guys know what, yeah, cosine. So therefore, couldn't I go ahead and say x is equal to r cosine theta? Couldn't I substitute? Which if you guys had this, you could do r cosine theta is equal to 10. Now here's a dealio. Rectangular. Here's what I need you to know for equation conversions. Rectangular would be y equals f of x, right? A rectangular equation, y equals f of x, y is the function. But what would a polar equation be? R equals f of theta? So if I want a polar equation, I need r by itself. I need r by itself. Yeah, good. All I have to do is divide by cosine. So r is equal to 10 over cosine theta, or 10 times secant of theta. I want you guys to go ahead and try in your graphing calculators if you can make that graph and see what it looks like. But then after you finish with making that graph and seeing if you can get your polar graphing to work, can you try to get this guy with r by itself? Can you try to get that guy with r by itself? Okay, try to get a graph in your graphing calculator. Then you can work in groups trying to change 2xy equals 1 No, polar mode. Yeah, people who were gone yesterday might need to reach out. We went in polar mode yesterday for graphing. So when you guys graphed the first one, did you get a line? Aha! What kind of line? Vertical or horizontal?
Vertical.
Sweet. That's exactly what you were supposed to get. But how did you guys try to get r by itself in this one? What could you have plugged in for x? Not just sine, though.
R cosine.
Yeah, you could do r cosine for x, and then what else could you do? For y?
Sine theta.
R sine theta. And then, well, 1 is 1. It's a number. It's no big deal. We just had to get rid of x and y. So now, what do I need to do? We could divide. What could we divide by? Yeah, we could divide by 2. We would get r squared cosine theta sine theta equals 1/2. And then what else could we do? Divide by cosine and sine, which would be 1 over 2 cosine sine. Oh, sorry, cosine theta, sine theta. They don't go together. They're two separate functions, right? Now, this actually is a special form, but I did tell you guys to get r by itself. So if I told you to get r by itself, what would you technically have needed to do? Yeah, and well, didn't we see that r could be positive or negative and still be okay? So therefore, we have to go ahead and do the plus or minus square root of 1 over 2 cosine theta sine theta. Now, is this one easy to graph? No, not necessarily. But if you were to do it, you should have seen, I think, well, let me see. I don't think this calculator actually does r squared. In other ones, you actually kind of memorize something to do with r squared, but this one you don't. It would be like your calculator. When you plug into yours, doesn't r have to be alone when you're in polar mode? Yeah. Okay. So I'm going to do the positive square root of, let's see, what do we have? 1 over 2 sine, and technically I could have done this in any order, cosine theta or sine theta. But that would have been the positive version of, oh, where is he? And then the negative square root of, except they don't like me. Why don't they like me? Use parentheses. Oh, they don't like this. Sorry. It's something to do with, woo, that got exciting. Whoop, that got exciting. Okay. They wanted some thetas in there. Let's go and get this guy in too. Whoop. 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 Okay. You know, as much as I want, no, I'm not going to. Okay, so, doesn't this look like a hyperbola? Or maybe some sort of rational function? It looks kind of like 1 over x, if you ask me.
Wait, but isn't that what theta is?
Isn't it y equals 1 over 2x? Doesn't that kind of make sense? Because we could have thought about this in function mode, which our brains are way more used to. And couldn't we have said y is equal to 1 over 2x, which is going to look something like that with a vertical asymptote at x equals 0? I guess that makes sense. Okay. Boop, boop. But what if I give you something like this and I say theta equals 2 pi over 3? Well, that's a little weird. I mean, we can still think about theta. We can think about x and y and r. We can think about theta. We can think about x and y and r. But if they want rectangular, well, guys, they've given me something with r's and or thetas. And this one's kind of awkward because it's just a theta. Kind of like an x equals doesn't have a y. It's possible in polar too. But I need to somehow get this to y equals f of x, right? I need to somehow get this to y equals f of x. So how can I get rid of a theta? You could do this a couple ways. Couldn't you actually graph this and figure out, isn't 2 over 3 this line? Oh, I just need a y equals mx plus b, don't I? And wouldn't it go through the 0? Wouldn't it go through the pole? So I could say y equals mx, because b is 0, but how do I know the slope? What did we learn in section 10.1 about the slope? M and, aha! I could say m is equal to tangent of theta, which is tangent of 2 pi over 3. So m is equal to, isn't that a 60-degree angle? And isn't tangent square root of 3 over 3? 30 degrees. 1, 45 degrees. Square root of 3. But it's second quadrant. And don't we know it's a downhill slope anyway?
No.
So we could say y equals negative rad 3x. But was there another way? Yeah. Isn't there in all of our equations, our conversions, isn't there a formula for tangent of theta? And isn't tangent of theta y over x? And couldn't I have gotten that to be negative rad 3? And couldn't I have multiplied x? Dun, 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 dun. Magical. How about number 109? How about number 109? It is interesting. I need to somehow get x's and y's in here. Is there any way to get rid of the r, get rid of the theta, maybe get rid of everything? I don't know. What do you guys think? Yeah, we could do that. We could do plus or minus square root, if you guys want. So we could do plus or minus square root of x squared plus y squared. I mean, I guess if we were going to do that, I guess we could have squared both sides. But we could do that later too, huh? I don't know. I guess we could do it either way. Here's the bummer. Isn't x and y having to do with the theta triangle? Not the 3 theta triangle? This is an example of how bad it can get. Not that it's actually going to get this bad, but it's how bad it could get. Do you guys remember way back when we actually talked about a way of breaking down sine theta? Maybe using something called the composite argument property? Sine of a plus b, sine, not co, not with or together, so therefore sine, cosine, cosine, sine, and sine, the signs stay the same. Oh, so I could make this 2. Sine 2 theta, cosine theta, plus cosine 2 theta, sine theta. Why on earth is this helpful? Can't I go one step further and say that this is equal to 2 sine theta cosine theta? And a cosine times a cosine would be a cosine squared theta? And then isn't there a double argument property for him too? That is, well, there's 3 different. Do you guys remember he was the or the or? What do we want? Cosine squared minus sine squared. 1 minus 2 sine squared. 2 cosine squared minus 1. 2 cosine squared minus, I'm going to do that one. 2 cosine squared minus 1. You're welcome. I'm just showing how nasty it could get. So then that's going to end up being 4 cosine squared sine plus, maybe I'll move them over there. I'll move them over there instead. 2 sine goes in, that'd be plus 4 cosine squared theta sine theta. And then the 2 sine goes in there, minus 2 sine theta. Oh, hey, those combine, that's pretty. So 8 cosine squared theta sine theta minus 2 sine. Why did I just do all of that work? All of that old school trig property, bleh. Because don't these use the theta triangle? So if they use the theta triangle, can't I go and say, oh, by the way, who's cosine? X over r. Who's sine? Y over r. Oh. So does that mean maybe I should have left the r in? Because maybe I have some more r's that are coming. So maybe I should have just left the r. I have some more r's coming, and they're going to come right now. Because I can go ahead and say, all right. So this is going to be 8 times cosine x over r squared times y over r minus 2 times x over r equals. I think I need to multiply everybody by like a r cubed maybe? Will that get rid of everything? So if I multiply this guy by an r cubed, and if I multiply this guy by an r cubed, and I distribute, that's going to be an r to the 4th. Those r cubes are going to cancel, so I'm just going to have 8x squared y minus, this one's going to be a 2xr squared. And maybe you guys could follow the algebra, maybe you couldn't, but if we get all the r's on one side, r to the 4th, 2xr squared, couldn't I pull an r squared out? That would be r squared plus 2x. Do you guys see how it could get hard? Trying to get r by itself? Oh wait, can't we just plug in stuff for r squareds though with x squareds and y squareds? Oh, maybe we shouldn't have done. Okay, I'm going to zoom back in. I'm going to finish that example. But guys, guess what? Homework doesn't get that hard. It's actually a lot easier. And homework is due tomorrow. Bye, guys. Homework is due tomorrow. If I'm going to come back here and be like, wait a minute, we know who r squared is. We can just plug in. Bye, guys. I'm going to leave him all nice and implicitly defined. Let me go pause the video, Kim.